Here we have four gases, and we know, according to the ideal gas law, what Avogadro told us, that if these are under the same conditions, that all these molecules have the same pressure, the same volume, the same number of moles, if they're under the same conditions. There's sometimes this doesn't apply, and that's what we're going to talk about today. Before we do, we're going to look a little bit at this distribution of velocity. We see at one temperature, all molecules are not moving the same, so we talk about the average velocity. But if we increase the temperature, you have a greater spread of those molecules. Notice on this, we usually think of temperature being on the y-axis. Here it is on the x. And so we see these molecules are moving the slowest. These molecules right here are moving the fastest. Continue. If you look at heavy molecules have the slowest velocity. Light molecules have the fastest velocity. Continue. So we talked about the assumptions of the kinetic molecular theory of gases. There are two here that don't apply. We're looking at ideal gases. One is gases consist of tiny negligible volume. That is not true under certain conditions. And next it says intermolecular forces of attractions do not exist. That is not true under certain conditions, and we will talk about that today. Notice you see here at low temps, gases are less distributed. At high temperatures, there's a much greater distribution. And so you have gases here at different temperatures. The kinetic molecular theory of gases, important thing to notice here is that they have the same average kinetic energy, which is the same temperature, but the ones with low mass are moving the fastest, such as helium, and the ones with heavy mass compensate that. Even though they're moving slower, they will have the same kinetic energy because they're heavier, and all that works out. The important thing we're going to discuss today is this formula right here, which is a van der Waals equation. What it does, it corrects for pressure with the A term, and it corrects for volume with the B term. So this pressure is actually the pressure that's observed, which is a little bit lower. We're going to add to that term because some of those molecules, because of intermolecular forces, do not hit the sides of the container. And the volume we're going to subtract from that because actually molecules under certain conditions, that space they take up is not negligible. So real gases can be very similar or very different from ideal gases because of these two things we discussed that don't always apply in the kinetic molecular theory. Gas molecules have significant volume. Gas molecules do have attractive forces for one another. This occurs when gas molecules are forced close together. When does this occur? At high pressure. Because under high pressure, you put gas molecules in a small space. And at low temperature. At low temperature, gas molecules are much closer together. So A deals with how strongly they're attracted to each other. So what happens when they're attracted to each other, they do not, gas molecules will act as one, and so gas molecules are not hitting the sides of the container as often. And B deals with the actual size of the molecules. Because of molecules have size, we're going to subtract from the volume, and you have to look up the A and the B values on a table for each specific substance. For example, if you look at this question, what is the pressure that exerted when you have 3 moles of chlorine gas at 4 degrees Celsius and 1200 torr? Now, one thing you might not notice is this is a very chilly temperature. This is actually negative 40 degrees Celsius. That's a negative sign there. And that's an extremely high temperature, 1200 torr. That's almost twice atmospheric pressure. So we're going to use the ideal gas law, and if you plug those things and determine the value, you'd find that the pressure was 5.74 atmospheres using the ideal gas law. But this is a problem where it'd be appropriate to use van der Waals equation because, one, it's a very chilly temperature, minus 40 degrees Celsius, and it's extremely high pressure, so those molecules are going to come in contact quite a bit. So with the van der Waals equation, we actually found the pressure is much lower because molecules are attracted to each other and there are not as many hitting the sides of the container. And also, the volume is a little bit smaller because we're going to subtract the space they actually take up. So because under these conditions, the gases do have attractive forces, and the space they occupy is actually significant. So if we look at the van der Waals equation, real versus an ideal gas, in a real gas, there is volume and intermolecular attraction. In ideal gas, we say there's no volume and no intermolecular attraction. So here we see the attraction and no attraction. And so What happens when you force molecules close together? There's more attraction, and we see that in this area right here. But under high temperatures, those molecules aren't close together, but if you decrease the temperature, they're going to be very close together. So we see molecules are close together, and then forces of attraction exist. When molecules are closer together, they condense, and intermolecular forces are stronger. So at the bottom, we see we have deviations from the gas law. One, because of pressure, and two, because of temperature. When you decrease the temperature, they're closer together. When you increase the pressure, the molecules are closer together. When you do that, they're attracted to each other, so there's fewer molecules hitting the sides of the container, making your pressure lower, and your volume is actually going to be different because the molecules actually do take up space. And one thing to think about is if I look at one gas under low pressure versus high pressure, if it's low pressure, let's say that this is a space that gas molecules actually take up. Under low pressure, that's not a significant proportion. Under high pressure, that is a significant proportion. And here we see some explanation of the deviations from the ideal gas law. Under this, we say there's a negative deviation, which you have presence of intermolecular attraction at low pressure and at high pressure. The difference in those two. At low temperature, there's a greater deviation, and what happens? PV over RT is going to be greater than 1. So this leads to a positive deviation for the volume of the molecules, and at very high pressure, the volume of the gas is significant. This is a comparison of a real versus an ideal gas. Notice the ideal gas, we're going to use the ideal gas equation. And the real gas, we could use an ideal gas equation as well, but it's going to give us a very different answer. In the van der Waals equation, we have the correction for the A and the B value. The A is a volume correction, the A is a pressure correction, the B is a volume correction. And notice the deviations are the greatest for the heaviest molecules. So for example, CO2 would have the greatest deviation from ideal behavior, and hydrogen would have the lowest deviation from ideal behavior. One final thing I'd like to point out here is notice the A and V values and the corrections are different depending on the particle. Notice A once again is a correction for the pressure. Notice A is a correction for how strongly the molecules are attracted to each other. So it's a correction for the pressure. Notice you see a small molecule, such as helium, does not have much intermolecular attraction, so there's not much of a correction value. But as you get to a larger and larger molecule, for example, water, which can hydrogen bond, has a very large correction value for the A component. As far as volume, it's simply size. Helium is a very small molecule, so even though you're going to use it, it's going to have less of a correction value than you would use for a larger molecule for water. So A, once again, is for intermolecular attraction, and B is significant for the amount of volume a substance actually takes up. So that's it for van der Waals equation. Let me know if you have any questions.